All right, my usual. Anybody want to start with a question? Something about 4.1 or 2 or 3? Graphing, different ways to graph these linear equations. All right, you're okay with that? So here we are. We're on to section 4.4. I want to point out right away to start, we basically have moved a day ahead as far as what I allowed for chapter 4. Last week we were kind of able to do 4.1 and 2 together, and I decided to move our test one class day ahead, which makes it happen next week Thursday rather than the following Monday. Now, the day before that Thursday is Veterans Day. There'll be no class that day, but I'll be around anyway, hanging out, looking for questions you might have. And as always, the class period before that, the Tuesday, is now scheduled, is the scheduled review day. So we'll finish up our material. Really, I've allotted 2 days each for the 2 topics after today. We'll finish it up next week, Monday, have a day of review. You actually kind of, if you want to use it that way, you almost get another day of review on Wednesday because there's no class, and then Thursday test. All right, now if there's any issues with that, please get back to me as soon as you can. And, you know, I'm kind of making this a change, you know, with less than 2 weeks to go. So, you know, if there's really a problem, please let me know and I'll consider it. But that leaves us more time for our last section, our last chapter. Basically always a good thing, I think. All right. So going on today, section 4.4, our concept is the idea of slope, or how slanted is this line? What's the rate of change? All right, start talking in those terms right away. So get my notes here, get ready to go here. I've already addressed it or mentioned it a couple of times, looking at the graphs that we've been making. And if I've got a line that I've somehow graphed from an equation, we can look at that and say, gee, I kind of notice it's going uphill, all right? It's got we'll say that has a positive rate of change, it's going up. Or I might graph one, it looks like it's going downhill. It has a negative rate of change. We'll talk about positive and negative. So slope is defined as how much does our value change vertically relative to how much it changes horizontally. We use a special letter. Of course, here we're talking about slope, okay? How slanted is that line? Don't get messy, Steve. We use a special letter M. That is, we use the letter M, or we reserve it to stand for the value of the slope when we eventually start working with equations and identifying the slope. Well, we've already written an equation form, like a formula, and I've called it y equals mx plus b. And that m is going to be this slope value. Now, I try to speak generally in terms of up and down versus left and right, or horizontal versus vertical, to help us remember that. The mnemonic device, rise over run. Sasha already mentioned that in a post yesterday, you know, using the slope value. How much did the value on the graph change vertically, right? How much did you change from one point to the next, going up or down? And we call it the rise. It's a mnemonic device intended to help you remember the structure here. The vertical change is on top, and the run is the horizontal change. Right? It is a ratio, right? A ratio of how much did the vertical amount change compared to the amount of horizontal change. So it's a ratio. And if we have different kinds of units, we call a ratio a rate, like, you know, miles per gallon, right? There's a rate. How many miles did you go per gallon? that will end up being a slope value in a problem. How, what great mileage do you get on your car or not, like my truck. All right, so the rise over the run. This is the general concept that we're going to try to quantify today. Well, if I'm looking at a graph, right? If I'm looking at a graph, I want to recognize or identify 2 points on that graph that have integer values. Find some nice points on your graph. And I just made up something here. I'm going to use that point and see if I can find one out here. It looks pretty good on my graph. All right, so I'm looking for 2 points on my graph. Now, just because you probably have a hard time counting my squares that are sort of non-existent, I'm just going to point out that this is the point 0, 2, right? And this, what did I do? 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. I call that 5, 5. Okay. So here are 2 points that I've identified on my graph. From this point to this point, how much did those 2 different values, the horizontal and vertical values, change? So to begin with, we can just count the squares. And especially if like you're looking at the text or something, it might suggest that, oh, draw a little right triangle in there to help you count them. So I could draw, let's see, 2, 3, 4, 5. I'm going to adjust my dot a little so it looks a little better, right? Draw a vertical. There's a line that represents how much it changed vertically. And there's a line that represents how much it changed horizontally, a little right triangle. Count the squares. The slope here, how much did it change in the vertical direction, the rise? From this point, I don't even really care about what the numbers are. I can just count my squares. If I know the unit value, of course, it's assuming, of course, my graph, they're all ones, right? 1 unit apart. Could be something different on a different context problem. But here I went 1, 2, 3. So vertically, I made a change of 3 units for a change horizontally of 1, 2, 3, 4, 5. Squeeze it in there, right? 1, 2, 3, 4, 5. I called it 5. So the slope, or the rate of change of this line, is this ratio 3 to 5, or 3/5. For every 5 units I travel horizontally, I'm going to change 3 units vertically. Now, I've talked about relationship in a line being kind of special in that that rate of change is consistent. If I can find any 2 points on this line, right? 1, 2, 3, 4, 5 should be one down here. And make it look right. From this point, if I go over 5, I went up 3. If I go over 5, I'll go up 3. So that rate of change is consistent. That's what makes it look like a line and not some other kind of curved shape. So we're going to identify the slope of our lines today. We start by identifying 2 nice points on our graphs to work with. Rise over run, if you're ever getting stuck, again, I always say, oh, it's a shame when I see it, a student makes a mistake and they get them upside down. Rise over run, it's intended to help you think, oh, rise, that's up and down, and run, that's back and forth, or something like that. So I can put any 2 points on my graph. If I can make them look a little better as far as my lines or squares on my graph. Here I just put 2 points on this graph. I started that way. I'll connect the dots and make the line. So some line goes through those 2 points. There's an equation that will describe that line. For your benefit right now, I'll just say, oh, that's the point 2, 0. And what did I do? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay. So what is the slope of this line? Just compared to that first one, it's steeper, right? And it's still going uphill. It's a positive slope. So we say it's going uphill, it's positive. We expect a positive number. Because it's steeper, we expect the value to be a larger value. 3/5 was our last one, right? This one I expect it to be a larger number, a steeper slope. So I'll draw in my little right triangle right now, just to help. And now I'm going to just count the squares. The slope of this line, the rise, the change in rise, again, I'm going up. So it is a positive change. I went up 1, 2, 3, 4, 5, 6. And how much did I change for my run or horizontal change? 1, 2. And there's a slope. For every 2 units I go over, I'll go up 6. It can be reduced. Just made it up, but we'll just see that written as a 3. Eventually we'll need to understand that kind of means 3/1. Right? I want to be able to see both the rise and the run values. So for every 1 I go over, I go up 3. Right? Over 1, 1, 2, 3. There's another point on that graph. All right? I go over 1, I'll go up 3. This line has a slope of 3. So it's going to do several of them, okay? And let's see. Notice it could be any 2 points, and I started with one that happened to be on one of the axes. Doesn't have to be. And just to make the numbers work out nicely, I'm putting, or make the dots work out nicely, I'm putting dots on first and then making my line. Usually you'll see your line and then you have to look for 2 good points. Don't assume the intercept is going to be a good point, like this one is in between integer values. You know, look at the squares and find a spot where that line really crosses right at those spots. And again, just because you probably have trouble counting my squares, 1, 2, 3, 4, and that's a 1, 1, 2, 3. There's a -3, and 1, 2, 3, 4, 5. We're not really even using those values right now. Now, just qualitatively, this line, what's the quality of this line? It's going downhill. It's going down. I expect this number to be a negative slope, right? A negative slope. Drawing my triangle this time, I'm going to go this way and that way. So starting from this point, right, how much was my vertical change, or how much did the rise change? Well, I went down 1, 2, 3, 4. There's my negative. I went down 4. I went -4. My horizontal change, what did I call that? Starting, anyway, 1, 2, 3, 4, 5, 6, 7. All right. So if I go over 7, I'm going to go down 4. You know, over another 7, down another 4 is going to find me another point on that line down there. You might just see this as the negative in front. We're going to have to address that at some point. Here's a negative fraction. How do I interpret the rise over the run? It's a division problem that gives us this negative value. One value is negative and one value is positive. It really doesn't matter which one is which. For example, let's say if I just decided I wanted to start here and count this way, well, then I'd be going negative run, right? Well, -7, but from this point to there, I went up +4. So there I have positive 4 divided by negative 7. I still get this same negative slope value. If I choose to read it, you might say backwards. All right. Big picture though, you want to be able to look at that and say, whoops, it's going downhill. I better get a negative slope for that one. All right. Watching my notes here. All right. Let's pull it out here. Again, here are 2 points. Whoops, where's that ruler? Now, then, and eventually we're going to come up with a little formula where we actually plug in the coordinates. I went from 3,2 up to 10,7. Could you calculate that slope value? Now, maybe it's hard because unless you put those exact points on your own graph paper right now. But the idea that asking you to try to do it yourself. First of all, I expect it to be a positive value. How much did I go up from here to here? Right? Yeah. And so I went 1, 2, 3, 4, 5. That's my rise. And from here to here, I went 1, 2, 3, 4, 5, 6, 7. A slope of 5/7. Right? Slope of 5/7. So this is this value that changes, you know, it qualifies or adjusts. If I put in some number into my equation, eventually I'm going to modify it by this value. We'll see that when we start working with the equations, I guess. All right. Now let's say I've got.
Hey, Steve.
Yeah. Yes. Yes.
Sasha just texted me and she said that her audio cut out. Could you let her in?
Thank you. I saw she was in earlier. Good. Thank you very much. Yes.
Yeah, no problem.
Good. Good. All right. Make sure she gets back in here. There he is. There she is. Hi, Sasha. Sorry, you had trouble. Glad you're back. All right. Yeah. Here's one of those special lines. Did a pretty good job of drawing it, I think. Which of those words do we use, right? Horizontal or vertical, right? Horizon. That's the way I learned it as a kid way back when. Oh yeah, the horizon is the horizontal one. How much is it slanting? 0. All right. Well, this number should reflect that. And we should somehow get a 0 for our slope. I could pick any 2 points on that line. I'm not even putting coordinates on it right now. But if I go from this point to this point, how much did I change vertically? What was my rise value? Well, it was 0. And let's say that's what is it? 1, 2, 3, 4, 5, 6. Slow down. The slope is 0 divided by 6. It's 0. Right? It's 0. Horizontal lines have slopes 0. Good. Making sure everybody was still in there. Okay. So mathematically, we can show, you might say, that the slope is 0. That's another one. Special one, all right? A vertical line. Again, recall I talked about this one last time, I think. Well, how steep is this line? It's so steep. We say it's undefined. You know? Well, how does that work with the numbers, you might say? So any 2 points on that line, well, how much did that change vertically? What was the rise from one point to the next? Here I went 1, 2, 3. Well, what was the change horizontally? None, 0. What's wrong with that? You can't divide by 0. Division by 0 is undefined. So that's where we get the idea that the vertical is undefined. And maybe mom wants you to say does not exist, but undefined, right? Undefined slope. There is no slope. Straight up and down. So vertical and horizontal, got to keep those two straight. Horizontal slope is 0. Vertical, it's undefined. Well, all right, that's a nice little helper mnemonic idea. But could we calculate that? Well, yes, we could calculate that if we just knew 2 points. And let's put one out here. This time I'm going to use the coordinates and say this is 2, 1, 2, 3, 4. 2, 4. So this time you need the coordinates, right? And what did I do out here? 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6. 8, 6. All right, so here are 2 points. If I know 2 points, and I'm not even looking at the graph, if I know 2 points, I ought to be able to calculate, you ought to be able to calculate the slope of a line that goes between those 2 points. I'll set you up a little bit in a word problem. You might get 2 data points in the middle of a problem. When I started, from this point, I was at this point. When I ended up over here, I was at that point. So I get an XY and XY. We have 2 points here. Well, we're going to reinterpret this rise over run. We're going to write a couple things here. So the rise, as you might say, a concept, is the difference or the change in the Y value. The change in the Y value is the definition of the rise, right? How much did it change from this Y value to this Y value? And the run is the change in the X value. In a word problem context, this might be time and cost or something, but still it's basically the change in the vertical quantity over the change in the horizontal quantity, whatever the units might be. All right, so then we get what we call our slope formula. Okay, slope formula. I'm going to put some abstract letters assigning this. This is a point, X and Y, and we'll call this point 1, X sub 1, subscript, right? Not an exponent. And it has the Y value, Y sub 1. Could be any point, right? So we call it point 1, X1, Y1. That makes this one point 2, X2, Y2. Again, could be anywhere. I can call it point 1, point 2. So my formula then refers to that, those symbols there. The difference or change in the Y value, usually write it as the Y2 value minus the Y1 value. It's a difference, a subtraction. And the change in X be the X2 value minus the X1 value. There's your slope formula. You need to know this concept and how to use that formula. I'm not sure you're going to get it on the test. Hopefully we'll practice it and use it enough that you can reconstruct it, at least thinking rise over run, change in y, change in x. Now, but I would always have to point out, notice the two values from one point are in the same position there. Like here I started with the 0.2 values, y2 and x2, and subtracted the 0.1 values, y1 and x1. I'll do it again and we'll see it really doesn't matter which order as long as you're consistent. The values from one point are together, you might say vertically, and the values from another point are together there. So now I can plug in these numbers. That slope, well, I do the difference in the y's, y2 minus y1. Make sure you grab the y value, the 6 minus 4. Okay, and the x values, 8 minus 2. Simplify, right? 2 over 6, call it 1/3. The slope of the line that would go through those 2 points is a slope of 1/3. Let's see, 1, 2, 3, 4, 5, 6, 1, 2, right? Over 6 up 2, if I just counted squares. But I can calculate it from 2 known points. If you have a graph to work with, and you can identify a couple of nice values on that graph, you can just count the squares. If you know 2 points and you're not really looking at a picture, if you know 2 points, x, y, x, y, you can use the formula and calculate the rate of change. For this problem, what is the rate of change in this problem? So then we just kind of start playing with points. Any 2 points I can put up here right now, we can figure it out. Here are 2 points that are on some line. What's the slope of that line? I have 1, 2, and 4, 5. All right, yeah, looks like it looks pretty good on my screen here. Here's my formula. You probably want it handy for a while till you get real comfortable with this, but make sure you put the y values on top. Difference in the y's. It doesn't matter which one, but I'm going to call this 1.2 and this 1.1. So change in y, right? 5 minus 2. Change in x. I started here with y, so I have to start here with x. Very important. 4 minus 1. So 5 minus 3 is a 2. 4 minus 1 is a 3. That line would have a slope of 2/3. Going up 2 for every 3 units. I'm going to do this right away. Yes, go ahead. Go ahead.
Where'd you get 5 minus? Where'd you get that 3?
I was thinking of the 3. Thank you for catching me there, whoever that was. My brain gets ahead of myself. Good for you. Good catch. I won't even say I was tested. Dumb joke. 5 minus 2. Boy, 3 over 3. There's a slope of 1. There's one mistake, Steve. Thank you very much, okay? Sorry about that. You could see where I was thinking it was going to turn out to be a 3, and I wrote a 3 already. You know, get ahead of myself sometimes. I'm thinking ahead, what's coming next? What's coming next? But I know it's not good to confuse you, is it? But, well, so moving on from that, let's try that again. I have 8, 5, and 6, 1. All right. 8, 5, and 6, 1. You know, something like that. What's the slope there? Well, it doesn't matter which one's which, and I'll do this one both ways to try to prove that to you. But just because I wrote 0.1, 0.2, you might say order left to right. Let's call this 0.1. Let's call this 0.2. Blah. Change in y. 1 minus 5. Change in x's. 6 minus 8. Now, slow down, Steve. Okay. Now, 1 minus 5, negative 4. And 6 minus 8, negative 2. Well, here's a division. Negative divided by negative, that's a positive number. 4 over 2. And I'm even going to bother to even hang on to that denominator for the time being. So we continue to kind of see the rise over the run. Okay. What if I had called the other point, 0.1 and 0.2? What happens there? So I started here for this version. Well, what if I start here? 5 minus 1. Got to start here again. 8 minus 6. And I'm going to get positive 4 over positive 2. The signs work themselves out. Negative, negative, positive, positive. I ended up at a positive value. So it's totally arbitrary which point you call 0.1 and 0.2. I kind of don't even like it. I saw in our text, it says, we usually read left to right. So call this left 0.1 and call this 0.2. Well, it doesn't matter. The signs make it always work out the same value. All right, here are 2 points. Can you set that one up and do it? The 0.37 and the 0.102. Can you plug those values into our slope formula and come up with the slope of this line? I haven't done this one. I just made up a couple numbers. Who's got a value for us? Brave soul. What'd you get? Anybody? Somebody?
Negative 5 over 7.
5 over 7?
Negative 5 over 7.
Negative 5 over 7. Thank you. We could wait a long time if I really did that a lot, right? Well, so I'm going to start here. Okay, I'm going to do 7 minus 2 and 3 minus 10. And 7 minus 2 is 5. 3 minus 10, I'm negative 7. So I totally agree. Thank you. Good job. The overall slope is a negative 7/5. If I put those 2 points on a graph, we'd expect that to be going downhill from left to right. Using 2 points, plug them into the formula and calculate your slope. Any issues there? Anybody? How about this one? 2 points. See something special in those 2 points? Change in y. 4 minus 4. Change in x. 6 minus 3. What kind of line is that? Looks like y is always 4. We can mathematically calculate and get that 0 for a horizontal line. You can imagine it now. I'm going to make one up, do it the other way around, right? Vertical. What do I have to do to make 2 points for a vertical line? Well, let's make them have the same x value. 2 points of the same x value. But go through the motions here. Change in y, 5 minus 3. Change in x, 2 minus 2. Undefined. A vertical line where x is always 2. Now I've used a whole bunch of positive numbers in my points, but it really doesn't matter. What if I have one over here, one up here? I'm just going to make up some. Let's see, that's -4, 1. And in fact, I'll put this one down here, okay? And we'll call this 1, 2, 3, 4, 5, 6, 7, -3. I can still do the same calculation. I just have to watch out for the minus minus. That's what happens when you've got some negative values in for your point values, right? So calculating my slope, change in y's, I'm going to say 1 minus a -3. Here's my extra parentheses for that negative number. And change in x's, -4 minus 7. So, got to be careful working with those negative signs or minus signs, right? Minus minus, remember, is the same as adding. Subtracting a negative is adding. 1 plus 3 is a 4. -4 and minus some more. Minus and more minus. That's -4 minus 7 more, -11. -4 11ths. So just be careful when you've got some negative signs in there. Work carefully with those negatives. Huh? Yep. Ready? Here we go. I'm going to erase all this for now. What if I know the slope and I know a point? I ought to be able to graph that line. If I know the slope and a point. This is going to be our situation from now on, actually, when we try to graph a line, and eventually when we try to come up with the equation of a line. We need to know the slope, and we need to know at least one point on that line. And then we'll see how we can use that information to not only graph today, but eventually to come up with the equation of that line. So let's say I know a slope value. And I know a point. Okay. I know one point that's on that line, and that line has a slope of 2/3. Well, all right, let's graph this line. I know one point already, 0, 5. Okay, I'm gonna go over here. 1, 2, 3, 4, 5. There's one point. I think this is kind of what Sasha was alluding to if you saw her post yesterday about using the slope to graph your line. Now, I can use the slope from that starting point. You always need a starting point. Use that slope to find a second point. So here's where I have to remember, oh, that rise over run idea. From that point, if I go up 2 and over 3, there should be another point on that line. Rise, I go up 2 and over 3. I'll say it's about right there. All right, 2 and 3. According to this slope, that's another point on this line. I can now connect the dots and graph that line if I know the slope and I know a point. I gave us a convenient axis point there, a y-intercept. Doesn't have to be though. But I'll do that again. A slope of 2 and a known point 0, 1. Because x is 0, that is the y-intercept. 0, 1. I know that point. My slope is 2. Here's why I've been writing those integer slopes as a fraction. Think of that as 2 over 1. So I can see the rise and I can see the run. All right. So from my starting point, if I go over 1 or up, I go up 2 or up 2 and over 1. Up 2, over 1, there should be a second point right there, and I can connect the dots. Use the slope along with a given point. Threw in some negative signs. Here's a point on some line, and here's that line's slope. What's special about that point? The y value is 0. It must be an x-intercept. Right? But there's a starting point, -2, 0. And now I want to start from there and use my slope to come up with a second point. This is a negative slope. I expect this line to look like it's going downhill. Here's where I was saying, okay, I got a negative fraction, which is the result of a positive versus negative division problem. So I have to choose, it doesn't matter. Let's do -3 over +4. And I'll do it the other way in a second. All right, -3 over +4. So the rise is actually a drop of 3. So from my known point, I'm going to go down 3, right? 1, 2, 3. Try to do it pretty well here. and then over 4. 1, 2, 3, 4. And there's a second point. And if I connect those dots, right? Yep, it's going downhill, negative slope. Well, what if I had decided, and sometimes it's convenient to do it the other way around. What if I was running out of space on this side of my graph? Wouldn't it be nice if I could find another point this direction? Well, let's think of that as 3 over negative 4. Still going to give me a negative overall value, right? So this is saying I could start that same point if I go up 3, 1, 2, 3, right? And I go negative run, 1, 2, 3, 4, cheat a little bit, right? I'm going to find another point, a second point. Nobody says it has to be left to right. It could be, right to left. It should be the same, a point on that same line. But I found the second point, and now I can connect those dots. But I used the slope. I happen to interpret it as a rise over a negative run. So we read a graph, pulled out 2 points from the graph, not actually pulled them out, but actually counted squares on our graph to come up with the slope. Then if we had the coordinates for 2 points, we could use the slope formula to come up with the slope of that line. And now we're using the slope along with a known point to come up with 2 points and graph that line. And a couple application problems usually get thrown in here. A highway. Yeah, hi. Changes. I'm copying a problem here, so let's get it right. And let's write this as rises, okay? It's going uphill. Rises 2 feet for every 50 feet of travel. For every 50 feet of travel, I go up 2 feet. What's the slope of that grade, right? Mount Sexton, you're getting there. It's like, oh, we're going pretty steeply uphill. So an application, it's describing the amount of vertical change and the amount of horizontal change. Well, the grade is another way to say the slope of that hill, right? We rise 2 feet. Oh, there's my rise. For every 50 feet of travel. All right. So there's my slope value, 1 for 25. So the grade is a 1 to 25 grade. Roof lines on buildings are often described as a 3-4. All right, a 3-4 might look something like that, your roof line. This is a 3 and that's a 4. Roof line, how steep, or a lot of those new nice ones with the, what's it called, those dormer windows, really steep roof lines. I think 1 to 2 might be the most, but 1 over 2. But back to this problem, part 2 of this problem, I took it out of the text. If you're approaching Mount Sexton, it says 6% slope. Most important on the downhill side, a negative 6% slope. Slopes are presented for highways as percentages. What's that percent slope? Can you convert that 1 to 25 to a percent? You can do it this way. What's sort of the definition of percent? Divided by 100. How could I I could change that to 100 pretty easily. Could you get there? 4% slope. And if it was going downhill, well, trucks are being careful, you know. 5-6% slope is pretty steep for trucks and the way their braking systems work. Okay. Threw in a couple of the, what do you call it, applications there at the end. So now we know how to calculate the slope of a line. If we have a graph to work with and we have 2 points to work with, we can calculate the slope and we can graph it if we know a starting point and a slope. Tomorrow, we're going to take the next step and say, if we know the slope and we know a point, we can write the equation of that line. And I've actually planned 2 days for that section and 2 days for section 4.6, just because there's lots of little parts to it. All right. So do your best to get started. 4.3 wasn't due today because it was originally scheduled in this week rather than last week. So 4.1 and 4.2 are due tonight. But, you know, of course, get 4.3 done and give 4.4 a try also. And I'll see you tomorrow for 4.5, where we start writing equations if we've got the right information to work with. Okay, guys, folks. All right, folks, you guys have a nice day. Send me any questions and I'll be checking back, of course, as I usually do. All right, good to go. Thank you. Yes, you're welcome. And I'll see you tomorrow then.